In this screencast, we will discuss the characteristic equation and its importance in controls. What we're shown here on the screen is a generic block diagram for a servo problem. Recall that a servo problem is a case where all we're interested in looking at is how changing the set point influences the variable being measured. So here, after doing block diagram algebra, you can find that the transfer function that relates the set point value to the output value can be represented by Km GC GV GP divided by 1 plus GC GV GP GM. The characteristic equation can be found in the denominator of this transfer function. This denominator, it does not matter if it is servo or regulatory. Where regulatory, we're looking at how a change in a disturbance influences the change in the output variable. The denominator will always have this form, which is 1 plus all the blocks that are in the control loop. So here we'll have GC, GV, GP, GM. These blocks can potentially change if you have a slightly more complicated process that you are trying to control. So the question now is why is this denominator so important? The reason why the denominator is so important in this characteristic equation, the answer really falls around stability. Recall that when discussing processes, that the denominator of those transfer functions gave a whole heck of a lot of information, which included whether or not the process oscillated and whether or not the process was stable. Recall the fact that positive roots in the denominator meant that your process was unstable. In other words, it would head to plus or minus infinity. And the presence of imaginary roots meant the fact the process oscillated. So this now becomes more important when we're talking about a controlled process, because in natural processes, there's only so much we can control. But here, what we're going to do is with this GC transfer function, we are explicitly selecting what values we're going to be using for Kc, tau I, and tau d, if tau I and tau d are necessary. So what this means is the fact that we have a lot of freedom in selecting what our denominator looks like. And by selecting what our denominator looks like, that is going to solely dictate how this process acts. Will it be unstable? Will it be oscillatory? So to look at this here, the question is what can affect stability of a controlled process? The answer is everything that appears in the denominator of our transfer function. So I've already just talked a bit about the controller. So the values, the parameters of Kc, tau I, and tau d for a PID controller have a great influence on how your process acts. Therefore, that is why there are a whole host of different recommended ways to tune controllers because of this issue. In addition, we also want to improve how the process responds, but one of the major issues in terms of picking appropriate parameters for a controller is to ensure the fact that your response is stable. So the controller represents what GC is. The second term in our denominator is GV. So therefore, the valve can affect our stability. So what this means is the fact that by switching valves from equal percentage to linear, or just replacing the valve, if you replace one valve with a slightly different valve, that can greatly affect the stability of the system. So therefore, what this means is the fact that any change to a valve that you make will require a change in your controller tuning parameters in order for this to work. That same logic goes for GP, the third part of the characteristic equation. So therefore, if your process undergoes any changes from its set points, that can lead to a requirement of changing your controller. The fourth and final part here is the sensor transmitter. So similar to the valve, if you have to replace your sensor and or your transmitter, that can potentially cause a change in the transfer function of the sensor transmitter, which can then lead to a change in your stability parameters, which would then lead in turn to having to change your controller. So the important part here is what the characteristic equation tells us is it dictates how stable the process is. And the most important thing that we can get out of the characteristic equation from a qualitative standpoint is that any change in any other transfer function in the control loop requires retuning the controller. Getting a new valve, getting a new sensor, your sensor being able to read over a wider range, a smaller range, changing the size of your tank in your process, changing the amount of liquid that you're holding in the tank in your process, changing flow rates. All of these variables can have an effect on transfer functions. And if they affect transfer functions, they're going to alter the characteristic equation. And if they're going to alter the characteristic equation, they can affect the stability of your process. In other screencasts, we will discuss the more mathematical approaches on how to handle the characteristic equation to more accurately say what ranges of controller tuning parameters we can have or not have.